We have seen the concept of integrating factors and examples of integrating factors also. We have also seen how to reduce a non-exact differential equation to an exact differential equation using integrating factors. But now the question is how to obtain these integrating factors. And there are some 4-5 rules or 4-5 methods of obtaining these integrating factors. Among them, in this presentation, we are going to discuss these 2 rules. If we observe carefully, the integrating factor is an exponential function e raised to integration gx dx, and here it is e raised to integration gy dy, where the gx and gy are such functions and they should exist for given differential equation, and then these are the integrating factors. You may feel that how can one think of such a complicated term as an integrating factor of a given differential equation? And answer of this how, that means idea behind these integrating factors, is here, and we start our presentation with that idea only. So let us begin with a differential equation which is mdx plus mdy equal to 0. Let us assume that some function f is an integrating factor of this differential equation. That means fm dx plus fn dy equal to 0 must be exact. Now this is exact means dabba by dabba y of fm should equal to dabba by dabba x of fm. Now f, m, n all are functions of x and y, and so we have to use product rule here. That means dabba f by dabba y into m plus f into dabba m by dabba y is equal to dabba f by dabba x into n plus f into dabba m by dabba x. This should be satisfied. Now, f is an unknown function. We don't know obviously then dabba f by dabba y and dabba f by dabba x, but we know m, n, dabba m by dabba y and dabba m by dabba x. So, to make our problem simpler, we put some condition on f, or we put some restriction on f, that f is function of x only. If f is function of x only, obviously dabba f by dabba y is 0, and this partial derivative is nothing but ordinary derivative of f with respect to x. So putting these values, our equation 3 becomes f into dabba m by dabba y is equal to df by dx into n plus f into dabba m by dabba x. Now if we take these 2 terms containing f together, we get f into bracket dabba m by dabba y minus dabba m by dabba x is equal to n into df by dx. That means our unknown function f, which is our integrating factor, is a solution of this differential equation. See, here we started at a differential equation which we couldn't solve, which we can't solve using our already known methods. So we want to find integrating factor, and our integrating factor is again solution of some differential equation. So we want to solve that differential equation to get that integrating factor. If all these terms are functions of x, then this differential equation is in variable separable form. But one thing is clear, that all these 3 terms need not be functions of x, because if I write the differential equation in this form, df upon f is equal to this bracket divided by n into dx, then this term should be function of x, and not all of them separately should be function of x. So, if the difference dabba m by dabba y minus dabba m by dabba x divided by n is a function of x, then this differential equation is in variable separable form. So, we put this another condition on our given differential equation, that if such a thing happens, or this condition is satisfied, then this differential equation becomes df upon f is equal to g of x dx, where g of x is that function. So integrating both the sides, we get ln of f is equal to integration of gx dx, and so f is equal to e raised to integration gx of dx. That's why such function is an integrating factor, provided this is true. That means if this condition is satisfied, we are getting this as an integrating factor. So one simple thing is, if we change x by y, that means why this f should be function of x only. If it is function of y only, then this dA by f by dA by x is 0. dA by f by dA by y is ordinary derivative of y, df by dy. Then we can take, or we have to shift this term here. Then it is f into bracket. Instead of this, it is dA by n by dA by x minus dA by m by dA by y. And we have to divide that term by m instead of n. Then in that case, that term should be function of y, and then e raised to integration gy dy is integrating factor. So both these rules, they are very much similar to each other, and we will see their detailed statements. So rule 1, for a given differential equation, if dA by n by dA by y minus dA by n by dA by x divided by n is function of x, then e raised to integration gx dx is an integrating factor. And the second rule is, if for given differential equation dA by n by dA by x minus dA by n by dA by y divided by m is a function of y, then e raised to integration gy dy is an integrating factor of the given equation. Keep in mind one thing, that already we have seen the idea behind these rules, but that is not the proof of these rules, of rule 1 or rule 2. In fact, if you want to prove this rule 1, you have to multiply this e raised to integration gx dx with this equation and show that it is exact, where your gx is this. And proofs of both these rules are explained in detail in another video, so you can check the proofs in that video. Now another thing is, you may feel that the rules are complicated somewhat. That means how to check these conditions and then how to decide whether we are applying rule 1 or rule 2. But if you look carefully, you can observe that, or you can recognize that the rules are not that much complicated. See, if the differential equation is given to you and if it is not in variable separable form, if you can't reduce it to variable separable form, you are checking exactness. And if it is not exact, or basically to check whether it is exact or not, you have to calculate dA by m by dA by y and dA by n by dA by x. And it is not exact means they are not equal. So consider the difference. And now check whether the difference divided by n is function of x, or the difference divided by m is function of y. And based on that, decide whether you are going to apply rule 1 or rule 2. Let me explain the procedure with the help of one example. So consider our first example, y ln y dx plus x minus ln y dy equal to 0 be our given differential equation. It is not in variable separable form. We can't use any substitution. So our aim here is y ln y. It is a product of two functions of y. So we have to use product rule. So dA by m by dA by y is y as it is into derivative of ln y, which is 1 upon y. So it is 1 plus ln y as it is into derivative of y is 1. So dA by m by dA by y, my is 1 plus ln y. Then take n. n is x minus ln y. So dA by n by dA by x is 1. They are not equal. So it is not exact. What is the difference? Their difference is ln y. Now observe m and n carefully. We can divide this difference by m, because ln y divided by y ln y, and we are getting function of y. That means we are going to apply rule 2. So for rule 2, we have to consider it is nx minus my divided by m, and it should be function of y. So it is nx minus my, so it is minus ln y upon y ln y, which is minus 1 upon y, and therefore e raised to integration minus 1 upon y dy, which is e raised to minus ln y, and which is 1 upon y, is our integrating factor. You may feel that why this order is important, because if we take my minus nx, then it becomes ln y. So just the difference of sign, and while integrating factor, difference of sign doesn't matter. But that is not the case. At this stage, it is the difference of sign only, but while integrating, it becomes e raised to ln y, which is y. and it's a huge difference, y and 1 by y. So be aware while writing this term. And you can remember that by using this simple trick. Whenever you are dividing by m, your function should be function of y, and the first term at the numerator should be nx. These are the relations between m, y and nx. Whenever you are dividing by n, your function should be function of x and first term should be my. So that order is important. Now since 1 upon y is an integrating factor, multiplying by that 1 upon y, our differential equation becomes ln y dx plus x by y minus ln y by y into dy equal to 0. Now, since this is an integrating factor, this equation must be exact. Okay, but always cross-check that whether it is exact or not at this stage. Why? Because if it is not exact, that means somewhere your previous calculations were wrong. Your integrating factor may be wrong. So at this step, you can cross-check your calculations, and that's why make it a habit that always check that the new equation is exact or not. Here dabba by dabba y of this is 1 by y and dabba by dabba x of this is also 1 by y, and so equation 2 is exact. Now apply our normal method of solving exact differential equation and verify your solution with this, that x ln y minus ln y bracket square divided by 2 is equal to c. See, I am not going in the details of this step now because we have seen so many problems of solving exact differential equation in previous videos. If you have any doubt, ask me on my mail ID, or you can revisit the videos on exact differential equations. So this is solution of my differential equation. Let us see another problem. 3xy minus 2ay square dx plus x square minus 2xy dy equal to 0. Let our m is, here our m is 3xy minus 2ay square. So dabba m by dabba y is 3x minus 4ay. N is x square minus 2axy, and therefore dabba n by dabba x is 2x minus 2ay. They are not equal. What is their difference? 3x minus 2x is x and minus 4ay plus 2ay is minus 2ay. So the difference is x minus 2ay. As it is, that difference is not divisible by m or n. But in n, if you take x outside, you can write our n as x into bracket x minus 2ay, and which is same as that difference, that bracket is same as. And that's why we can divide by n and we are getting a function of x. So we are applying rule 1. Since we are dividing by n, our first term at numerator should be my. So it is my minus nx divided by n. The difference is x minus 2ay divided by x into bracket x minus 2ay. So it is 1 by x, which is a function of x. And so e raised to integration 1 by x dx, which is e raised to ln x, which is x, is our integrating factor. So multiplying by x, we get the differential equation as 3x square y minus 2axy square dx plus x cube minus 2ax square y dy equal to 0. Again, as I said earlier, check whether differential equation 2 is exact or not. What is partial derivative of this term with respect to y? It is 3x square minus 4axy, and partial derivative of this with respect to x, 3x square minus 4axy. Since they are equal, the equation 2 is exact, and using our normal method of solving exact differential equation, we get x cube y minus ax square y square equal to c is our general solution. For this problem, it is homogeneous also. So you may try the substitution y equal to ux. Try that. Check whether your answer is same with this answer or not, and then decide which is simpler. This method is simpler or that is simpler. In the exercise, 4 differential equations are given to you. In the last equation, initial condition is also given to you. So you have to calculate value of C also. That means it is an initial value problem, IVP. If you have any doubt regarding exercise or regarding the discussion in the video, you can mail me on this mail ID. In the next video, we are going to discuss another rules of obtaining integrating factors of a given differential equation. Till then, bye. If you like the video, subscribe the channel, share it with your friends. Thank you.